looks like we're live. We're just going to give people a little bit more time to log in. And today's warm-up is 117. And it reads, number 1, solve graph, write the solution set and write a statement for number 1, which is 42 is less than or equal to negative 8 times the absolute value of x plus 3. Number 2 reads solve, and then we have x squared equals to 121. Number 3 reads write the imaginary number of square root of negative 81. And number 4, it says given the sequence, write the explicit rule, use the rule to identify the number of terms in the sequence. And the numbers in the sequence are 1, comma, 3, comma, 9, comma, dot, 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 729. I'll give you guys some time to work on that, copy that, then we'll go over it together. And that gives people time to log on, those that are going to join us. I hope everybody's doing all right, enjoying your work at home. Bam, let's go. Alright, so let's go over number 1. And number 1, we need to solve this inequality. So let me make some space here. Here we go. So I need to isolate the absolute value, so I divide by negative 8. Divide by negative 8, a giant 1 right there, so I have negative 6 is greater than or equal to the absolute value x plus 3. And just remember, guys, that whenever you are multiplying or dividing by a negative, to flip the inequality symbol. So do we have the absolute value by itself? Yes. But what do you guys notice? Once again, we have a red flag. What is our red flag? That this side is a negative. And what did we say when we get to these two? Read it and analyze it to see what we got. Over here we have a negative, and over here we have an absolute value. What do we know about absolute values? That everything is in distances. That's why it's a positive. And let's look at the inequality symbol. The inequality symbol reads greater than or equal to. And question, are negatives greater than or equal to positive numbers? No, that's why that is not true. So no solution. Hopefully you remember that. All right, let's go to number 2. Number 2, to solve, we need to isolate x. So what do? Square root of this side, square root of that side. We end up with x equals plus minus 11. Square root of 121 is 11. All right, let's go to number 3. It says write the imaginary number. So let's rewrite this first. This is square root of negative 1 times square root of 81. So what is square root of 81? 9. And what is square root of negative 1? I. There you go. All right. And let's go to our last one of the warm-up. It says write this. Given the sequence, write the explicit rule. Well, let's find out what kind of sequence this is. So from here to here, from here to here, from here to here. Well, not from there to there, but I'm saying in between. Let's see. Up to right there. What's happening? Yeah, it's multiplying times 3. Or another way of looking at it is, what is 9 divided by 3? 3. What is 3 divided by 1? 3. Yeah. So that means if it's multiplying or dividing, that means this is our R. If it's an R, that means this is a geometric sequence. So what's our explicit rule for geometric sequences? So g of x equals a times r and n minus 1. Let me change this really quick. Let me change it to f of n. There you go. Alright, so let's substitute values. We know that our r is 3. That goes right here. Times, and what is our a? Our a is our first value, which is 1 for the first term. And then we end up with f of n equals to n minus 1. Alright, so whatever we get here, we're going to end up multiplying times 1, which means, do we need to write the 1? No. So then it would be f of n equals 3n minus 1. So how do we figure out how many terms? That means that the n is the term that they want us to figure out. So we go with our last term, which is 729, and we substitute it here for f of n. So we have 729 equals to 3n minus 1. So what does that mean, Mr. Q? Well, that means that we need to rewrite this number to the same base of this one so that we can see that the exponents match, or to see what the exponent is going to be on this side with the same base. So if we're going to make it to the same base, we're going to do a factor tree here using base of 3. So 729 divided by 3. 3 goes into 7 2 times, carry 1. 3 goes in. Alright, so if we have 1, 2, 3, 4, 5, 6 factors, that means we can write 729 as 3 to the 6th power. Because we have 1, 2, 3, 4, 5, 6, and base of 3. And what's this side? We have 3 to the n minus 1. So now that we have the same base, do you agree that 3 is the same as 3? Yeah. So if we agree with that, that means that this is the same as that. So we can write here 6 equals to n minus 1, and it's solved. Plus 1 plus 1, 7 equals n. And this one tells us how many total terms does that sequence have, all the way up to 729. So we just write the sequence has 7 terms. 10 cubed. Alright, so let's move on. Our home play for tonight is on page 714, all only. Alright, here we go. Our objective for today: I can write and graph exponential functions. I can write and graph exponential functions. So if you notice, we're still on the same concept, exponential functions, and we're still graphing and writing. So by now you should know how to fill this out by yourself, and I'll give you that to do by yourself without looking at your notes and so on and so forth. And then we have our general transformation rule, just to kind of like recap. And then from there we got to our general transformation rule for exponential functions, which is that. And we did plenty of work with this. And today we're going to take a little step. I'm going to say sideways, so that we can take a break from doing all the transformations. But we're going to be writing now functions given data. Like I said on Tuesday, that now everything that we've done, we're going to apply to modeling and stuff. But once again, I want to get you closer to refreshing some of the things that we've done in the past, and hopefully you remember. Okay? So quick recap. Remember when I asked you for the explicit rule for geometric sequences? We did first arithmetic and geometric, but then I said we're going to focus from this point forward on geometric sequences, which led us to geometric series. So therefore, explicit rules. If n is starting from the 0 term, remember the table? If we started with a 1 on the end and then they give us a number, but this one was if they start at the 0, that means our function is f of n equals f of 1 times r to the nth power. And then if it was starting from the first term, it was f of n equals f of 1 times r to the n minus 1 problem. And this one, the second one, looks familiar because it's the one we've been using for the warm-up. But I said from now on, instead of f of 1, which we understood it was the first number on the first term of the table or the sequence, now we labeled it what? A. Same thing with this one. Instead of f of 1, we label it A. So earlier in the warm-up, which one did we use? The second one. We started from term 1. They didn't give us a table. They didn't give us that it's starting from 0. That means we assumed that it was a first term, and that's why we use this one. All right. But today we're going to be focusing more on this first one because we are going to start with n greater than or equal to 0. We're going to start from the 0 term. And most models, guys, if you've been watching the news when they present like the president or the governor of California, when they present the data in regards to what's going on with all this stuff in regards to the COVID-19, they always start the graph. I don't know if you notice, starts going upward, but they always start from 0 over here. And that's why we're going to focus on this piece. Okay? So, and there you go. Some of you ask me, Mr. Q, when are we going to use this? Well, in life. Well, they've been using it in life and in the news. So you can actually do this part by yourself if you want to make it a family math night over the weekend, over the spring break. Bam, get some of those graphs from the TV and do this activity that we're going to do today. So to get us closer to where we're going, copy this one, example Q, and it says write a rule for the given data. And we've done this in the past, but like I said, I'm bringing it back just to get us close to where we're going. And it says write a rule for the given data. And the table given is x and f of x. And for x, which is a domain, they give us the domain 0, 1, 2, 3, and 4. For the f of x, which is a range, they give us 1, 4, 16, 64, and 256. All right? So, to get started, let's see what's going on here. Now, we're going from here to here, from here to here, from here to here, from here to here. So, let me show you another way of presenting this. From here to here, I can write 4 divided by 1. From here to here is 16 divided by 4. From here to here, 64 divided by 16. And from here to here, 256 divided by 64. What am I doing? I'm taking this one divided by that, and so on and so forth. So let's see. What is 4 divided by 1? 4. 16 divided by 4? 4. 64 divided by 16. And 256 divided by 4? Yeah, 4. So what can we conclude? Since it's dividing or multiplying, that means this is our r. Our r is 4. All right, but what do you guys notice? Our a is 1.